So our next topic here is going to be on covalent bonding. So we said that with ionic bonding is that one atom completely steals an electron from the other, or several electrons from the other one. And this happens if you have a very large difference in electronegativity. But if two atoms have only a very small difference in electronegativity, the more electronegative atom cannot remove the electron from the less electronegative atom, so it's impossible for an ionic bond to form. These atoms can, however, share their electrons to form a covalent bond. Remember, they still want to fulfill that octet rule, is that, you know, if I have something like aluminum and phosphorus, okay, the aluminum and the phosphorus right here, aluminum has 1, 2, 3 electrons, phosphorus, valence electrons, phosphorus has 1, 2, 3, 4, 5, should be 5, and I just didn't draw it right because it doesn't want to have them there. Remember our Lewis structure rules, you never double up until you have to. So phosphorus has 5 valence electrons out here. Phosphorus still wants to gain 3, so it wants to gain 3. Aluminum to get its octet. Aluminum wants to lose its 3, but phosphorus isn't strong enough, doesn't have a strong enough electronegativity to actually just take the electrons from aluminum. So instead what they're going to do is they're going to share them. And so we'll look at how that happens in just a second here. So covalently bonded atoms will share the number of electrons needed by each to fulfill the octet rule. And so that's sort of how that'll work. So let's just give an example to help understand how this occurs. So let's suppose we have 2 hydrogen atoms. So that's what we have down at the bottom. You can see they've got 1 proton in the middle and 1 electron that's out floating about in the electron cloud. Once again, it's not exactly this precise location because we can't know the exact location of electrons, but we can sort of describe as their orbital that's out here. We can see the 2 orbitals, in this case 1s orbitals that are out there. So I'm going to erase this really quickly just so we can see keep up with what's going on. But basically this is what we have for our 2 hydrogen atoms, 1 proton, 1 electron. So they're the same element. They have exactly the same electronegativity, and so they will definitely not form an ionic bond because they have to have at least an electronegativity difference of 2 to do that, and these have an electronegativity difference of 0. So each hydrogen atom has a single electron in its 1s subshell. So if these 2 hydrogen atoms get close to one another, here's what's going to happen, is the electron of one is going to attract the proton of the other one and vice versa. And the same thing will happen here. Even though that electron's not in a specific spot, they will attract simply because of the fact that the part of the electron cloud that's out here is closer to the nucleus than the nucleus is from the other nucleus, which would repel. And so this is going to pull these 2 atoms together. All right? So what happens here is when they get close enough, if the electrons of each atom have opposite spins, one is spin up and one is spin down, when they get close enough, they will occupy the same overlapping 1s orbital. So in this case, instead of having 2 separate 1s orbitals here, these have really combined into a single 1s orbital that surrounds both of them. This is technically called a molecular orbital. We won't talk about this here in a lot of detail, but all you need to know is that they now have their 2 electrons are both occupying the same 1s orbital. And they only do this if they have opposite spins. If they have the same spins, this doesn't work. But if they have opposite spins, they can occupy the same 1s orbital. Now, that electron pair is now shared equally between the 2 hydrogen atoms. We would not say that this electron is just sort of being like temporarily loaned to this one and this one's being temporarily loaned to this one. No, they share them equally. This is a completely equal partnership in terms of what's happening with these 2 because of the fact these 2 hydrogen atoms have the same electronegativity. And so now these electrons are going to tend to sit in between the 2 protons that are in here. The reason why is that because if you remember, these are negative electrons, they're attracted to the positive protons. And so if they sit sort of in between, then they are able to get close to not just 1 positive charge, but 2 positive charges. And that means they're able to lower their energy. And if they lower their energy, then, hey, this is a more stable situation. Remember, the atoms will bond in order to create this lower energy. But second thing, look what this does to these 2 atoms, is that this positive nucleus that's right here is now going to be attracted to this electron pair really strongly because now there are 2 positives that are pulling it towards it. And this positive nucleus from the other hydrogen atom is also going to be attracted together. This causes these two nuclei to stick together and forms what we call a covalent bond. So they sort of hold it together. They act like that sort of glue-ish type stuff. I mean, really, it's just a positive-negative attraction between the two electrons that sit between the two protons that now exist in the same overlapping orbital. So this doesn't have to just happen with hydrogen. This can happen with other things too, other elements too, as long as the electronegativity difference is not greater than 2.0. So in covalent bonds, atoms share pairs of electrons when both atoms have unfilled orbitals by overlapping the orbitals, okay? So it only shares pairs. They don't share one electron at a time. They do occasionally, but very, very rarely, and it's sort of beyond this course in terms of when that happens. But generally, atoms share electrons as pairs. One donates one donates the other, and they share both pairs together here. And it only happens if you have unfilled orbitals, or generally happens by having unfilled orbitals whenever the two unfilled orbitals overlap each other and become one larger orbital. All right, so if two atoms share one pair of electrons in an orbital, just one pair in an orbital, we call it a single bond, okay? So that would be a case like, for example, that hydrogen is those two hydrogen atoms. If we were to sort of draw out this, we'd say the Lewis structure is that each one has one electron. They want to have a full octet. Now, in this case, their octet is not 8 because if you look at hydrogen, what's the nearest noble gas to hydrogen on the periodic table? It's helium. Helium has 2 electrons because you can only fit 2 electrons in the 1s subshell, or the 1s shell, or the first energy level, sorry. And so it really wants to have 2. And so how is it going to get 2? Well, what's going to happen is that these 2 electrons are going to move over. Oops. Let me get the one I wanted here. They're going to move over, and I just erased half my H, so that they are now being shared between these 2 hydrogen atoms. And so one way we draw this out is by drawing a single line between them like this. And so that single line that we have is called a single bond because they're sharing one pair of electrons. Okay? Now, sometimes what will happen is you'll have 2 atoms share 2 pairs of electrons in 2 different orbitals. So, for example, classic of this one would be oxygen gas. Oxygen gas that you breathe in is not just one oxygen, it's actually 2 oxygen atoms that are bonded together. And so here's the way it works. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6 like this. And so what happens with the 2 oxygens is that each oxygen, they're both oxygen, they have the same electronegativity, they're not going to form an ionic bond, they're going to share their electrons. Now oxygen, if you look at its electron configuration, the last term in it is going to be 2p4. And so if you were to draw out what oxygen would look like here, you'd say, hey, it's going to be, so 2p has, since it's a p orbital, has 3 orbitals here. 2p subshell has 3 orbitals here, and so if we draw out oxygen, we'd say it has 1, 2, 3, 4. But you notice, to get that full octet, oxygen's going to need 2 more electrons, 1 to go into this orbital and 1 to go into this orbital. And so it has 2 orbitals that are partially filled, right? These 2 right here. What about the other oxygen? It's also going to have 2 orbitals that are partially filled. And so what's going to happen is that these 2 oxygen atoms are going to move together so that this orbital and this orbital overlap one another, so that now that the oxygen atom, the electron from one of them is going to be shared together, the electron from the other one is going to be shared together, and vice versa, so that now both oxygen atoms have a full octet of electrons, and now they're sharing 2 pairs of electrons in 2 different orbitals. And so in this case, we would call this not a single bond, we would call this a double bond. It's going to be not just sort of a double bond, it's also going to be a stronger bond, it's going to be a lower energy bond, and it's going to be a more stable bond. So whenever this oxygen that's in the air are really tightly bonded to these other oxygens. Now, it's possible to even go farther than that. If 2 atoms share 3 pairs of electrons in, that shouldn't be 2, that should be in 3 orbitals. 3 orbitals, the bond is a triple bond. An example of this would be the other component that's mostly air is made of is nitrogen. Okay, nitrogen, if you take a look at it, has 5 valence electrons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, like that. You can see that other one right in there. So 5 valence electrons. They want to have a full octet. They need to gain, each one needs to gain 3 more. But how are they going to do that? Well, if you look at what the orbital box diagram is for nitrogen, we look at its 3, it's got electrons in the 2p. And if you look at where it is in the 2p, it's got 1 in each box because it's going to go 2s2, 2p, 3. And so because of the fact that there's 1 in each box, it has 3 orbitals that only have 1 electron in it, and so these 2 nitrogens get close enough, they will overlap all 3 of their orbitals. That nitrogen number 1 will overlap each of its orbital with the ones in nitrogen number 2, and as long as the electrons have different spins, so they have to have different spins, that now they're sharing 3 pairs of electrons. Now this is the triple bond, extremely, extremely strong. So triple bonds are more stable and stronger than double bonds. Double bonds are stronger and more stable than single bonds. Also tend to be much shorter. So we can sort of look at a little bit about how this works in terms of why that those bonds tend to get shorter when they're lower energy with this. And this is an energy diagram. And so this potential energy or the chemical energy that we have here is showing how much energy that the 2 atoms have. In this case, what we're looking at here is H2. We're looking at hydrogen right here. And so these are the 2 hydrogen atoms. And so whenever the hydrogen atoms are far apart, they tend to have a higher energy. You can see the energy right up here is high. But as they move closer together, that energy drops, okay? And it drops down until it gets to this point right here. At this point right here, we have a situation where those hydrogens have their electrons in the orbital in between them, and so the positive that's in the center of this, that's the proton in the middle of the hydrogen atom, is attracted towards the electrons here, and they both attract towards each other. Whoops, they both attract towards each other like that, and so they reach a nice stable spot down here. And that stable spot, the distance that they are away from the nucleus, is called the bond length. And that bond length in this case is 74 picometers. That's the actual length where hydrogen atoms are most stable. But what if you were just for some reason to try to force these guys together even stronger? You're going to take these 2 hydrogen atoms and you're going to jam them together even farther than what they are here. Well, what would happen at that point is that these 2 positives would get so close to one another that they would start pushing back out. And so as a result, you would be less stable. And so if you try to get this hydrogen atom up here, if you try to move them too close to one another like that, then they actually start pushing out on each other. They're not nearly as stable anymore. And so if they're too far away, they're not stable. They want to come down and get more stable. If they're too close to one another, they're going to try to push apart and get more stable here. And they're going to go until they find that nice, happy spot where they're just at the right distance from each other, where they share those 2 electrons in that same orbital that hold them together. And so that distance is the bond length. If you have a double bond, then this drawing right here wouldn't happen for hydrogen, but if you had it happening for something else, would not look the way it does right now. It would look deeper. It would look more like this. And so in a double bond is that you are sharing 2 electron pairs, and so sort of the pit is deeper, the energy pit. They're at a lower energy. You can see this energy is at 432 kilojoules per mole. Is basically the energy of that bond, versus this one is going to be over negative 500, so it's lower energy, so a smaller energy here, which means it's more stable. And when that happens, I didn't draw this very well, but actually this really should have been more like this. This middle part here, where this comes together, is actually closer. It's a shorter bond length. So tighter bonds have lower energies, are more stable, and tend to be shorter. And double bonds are going to be shorter and stronger than single bonds. Triple bonds are shorter bonds and stronger bonds and more stable bonds than double bonds. So, unlike ionic compounds, in which atoms bond with all the oppositely charged ions which surround them, covalent compounds, the bonding only occurs with atoms with a shared electron pair. And so if I have a hydrogen gas, is that my hydrogens are going to sort of pair up as they share electrons this way, but they will not form bonds, really, not chemical bonds, with these other hydrogens in here. That's not going to happen. The reason why is because they can't. They've only got 1 set of electrons they can share. And so those are the ones that get shared just between the two pairs of hydrogen atoms here. And so, you know, that's why the covalent, we ended up with this giant crystal structure, this lattice, where we alternated positive, negative, positive, negative, positive, negative ions. That doesn't happen with covalent bonding. We end up getting groups of atoms that share electron pairs with each other. And so, even if we do have other atoms nearby, if there's no electron pair that's shared, there is no bond that's formed. It only happens whenever they share these electron pairs. Now, covalent compounds then, therefore, don't form crystal lattices like ionic compounds do. Instead, they form molecules. And so molecules, only a few atoms are bonded together with each other. And so we say a few, sometimes it can be only just two, like for example, hydrogen. And you can have much, much bigger molecules, like for example, DNA. For that's an extremely, extremely large molecule, but still each atom is only bonded to the atoms, covalently bonded to the atoms that are next to it, because they share electron pairs, and then those connect to other atoms and they form chains in that case, but they don't form these big crystal lattices. And so next thing we need to know about this is, because this is true, they form these molecules that are tightly bound together, but they don't form chemical bonds with other nearby atoms that do not have shared electron pairs. The forces between covalently bonded atoms inside the same molecule are strong, but between atoms which are in different molecules are much weaker. And so the ones that are inside, these are the covalent bonds. The ones that are outside, there are some forces between them, but they're much weaker. They are the intermolecular forces that we will cover in a future unit. So let's look at what would happen here. So let's get hydrogen fluoride. So hydrogen fluoride, if we were to write this out, hydrogen is H, fluorine is F. Now the first thing we're going to need to do here is we need to establish whether or not these are going to be ionic or covalent. And so to do that, we've got to look at the ionization energy, or not the ionization energy, the electronegativity. And so I don't have the chart down here, but I'll write down what it is. So if we look up for hydrogen, the electronegativity for hydrogen is 2.2. The electronegativity for fluorine is 3.98. So to figure out whether or not these are going to form covalent bonds or not, we take the difference. 3.98 minus 2.2 is less than 2, so they will be covalently bonded. And so that means they will share an electron pair if they bond. So to figure out how they're going to share this electron pair, let's sketch out what we've got here. Hydrogen is going to have one electron right here. For a valence electron, fluorine is going to have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And so fluorine is going to get its full octet, is going to want to gain 1 electron. Hydrogen is going to want to lose its 1 electron. And so in this case, though, because they're not ionic, hydrogen won't full out lose it. It'll just share it. And so what we're going to have happen here, and so I'm going to switch the colors here just so we can see what happens, is that I've got my hydrogen right here. It's going to have its electron right here. I'm going to take my fluorine right here. It's going to have its electrons, 1, 2, 3, 4, 5, 6, 7. And so in this case, that these are a shared pair between the two. And so we'd overall going to end up with a single bond between the hydrogen and the fluorine. And so that's how these are going to covalently bond. Let's look at water. So water, that one we sort of know right off the bat, H2O. H2O. And so let's figure out how this is going to work, is that we have 2 hydrogens and 1 oxygen. The hydrogen over here, I'll try to use our color system. So hydrogen right here is going to have 1 electron right here. Oxygen is going to have 1, 2, 3, 4, 5, 6 valence electrons, and then we'll do our next hydrogen over here. It's going to have 1 valence electron, but are they going to actually form an ionic or covalent bond? We know they're water molecules. We expect them to be covalent. Let's double check and make sure. It said hydrogen, again, has an oxidation number, or it's 2.2 for its electronegativity. Oxygen, we looked that up, has an electronegativity of 3.44. Difference is less than 2, and so these will be covalently bonded. And so since they're covalently bonded, they will share electron pairs. And so the way this will work is that oxygen has 2 2p orbitals that are available that have just one electron in each one. Hydrogens have 1s orbitals that have one electron in each one, and so those are going to overlap. The 2p of each, two of the 2p's of the oxygen, and then one of the 1s for each of the hydrogens. This is what's called a hybrid orbital. Once again, not something we're going to talk about in this class, but it is possible to actually overlap orbitals from different subshells. So then the H is going to go here, it's going to put its electron in here, this H is going to go here, it's going to put its electron right there, and so then we're going to have two shared. We have these two are shared between the oxygen and the hydrogen, we have these two shared between the oxygen and the hydrogen. So here's the question, is this a double bond or a single bond? Well, this is actually a case where we have two single bonds. Okay, because if we actually look at this from the perspective of even though the oxygen is sharing two pairs, it's not sharing two pairs with the same with the same atom, and so as a result, we wouldn't call these double bonds, even though oxygen has two bonds. We would just say oxygen has two bonds, and but it's just there's a single bond with one hydrogen, a single bond with the other hydrogen, and so this would be a covalent bonding for water. Let's look at oxygen gas. We already looked at oxygen gas. We're going to look at it again. So oxygen gas, we have two oxygens. Are they going to covalently bond? Well, we first go and look at the, well, we know they're going to covalently bond because of the fact they're both oxygen. They have to have the same electronegativity, which means electronegativity difference is 0, so they must covalently bond if they bond at all. So in this case, we're just going to color them different just so we can sort of see what's going on here. This oxygen is going to have 1, 2, 3, 4, 5, 6 valence electrons. This oxygen is going to have 1, 2, 3, 4, 5, 6 valence electrons. And so they each have two shells that need two more electrons to get that full octet. And so what's going to happen is that these are going to come together. And I should have used different colors on those, but I will try to do this out this way. I'm actually going to tilt these back a little bit. See if I can get this to work a little bit better here. I'm going to put the other oxygen sort of down here just to show you how this is going to work here. So far, oops, I did the wrong color again. Let me try that again. Just so we can tell which ones originally came from which ones here, even though, of course, once they're actually shared, they're completely shared. They're not loaned. So we're going to have one from this one and one from this one. And so what's going to happen here is this one's going to put one right here, this one's going to put one right here. And so here are two pairs. This pair is shared, this pair is shared. Now if you notice, what this does is that now these two oxygens have two shared pairs. And so as a result, the two oxygens are going to create a double bond between them right here. And so this is a case where you have a double bond because of the fact there are two pairs of electrons that are shared between these same two atoms. So let's talk about polarity. So we've said that if the electronegativity is less than a certain amount, then you'll have a covalent bond, but not all covalent bonds are alike. Remember we talked about these polar and nonpolar solvents when we talked about ionic substances? Well, this is sort of where this comes from. Why is it some molecules are polar and some are not? So if the two atoms involved in a covalent bond have exactly equal electronegativities, like they're basically the same element, like two hydrogens or two oxygens or two fluorines, then the electron pair in the covalent bond is shared equally between the atoms. And so this little cartoon sort of shows you an example. Hey, we have two little hydrogen cowboys here playing tug of war, and because they each pull equally, they have the same electronegativity, the same attraction of electrons, they share that electron pair. They're halfway in between. They're both happy because that's going on. They're not really happy because they're atoms, but you get the idea. However, if electronegativities are different, even if they're just a little bit different, but really it's the more different they are, the more this happens here, the more electronegative element will pull the electron pair closer to it than the less electronegative atom. So here now we have at the bottom hydrogen and chlorine. So hydrogen, if you look at it, has an electronegativity of 2.2. And chlorine has an electronegativity of 3.16. And so not enough to be ionic, that's not a difference of 2, but you can definitely see that chlorine has a much higher electronegativity than hydrogen does. And since it has a higher electronegativity, it's more attractive to electrons. So it doesn't have a high enough electronegativity to full out steal hydrogen's electron, but it's strong enough that it's going to pull it closer to it. And so those electron pairs end up actually sitting a lot closer to the chlorine than to the hydrogen. And if you think about this, this makes sense. That chlorine has an effective nuclear charge of +7, and the hydrogen only has an effective nuclear charge of +1. And so if I were this negative electron here, where do you think you'd want to go? You'd want to be a lot closer to that 7. That pair is going to be over here and a lot farther away from the 1 because of the fact that you're attracted more to those 7 protons than you are to the 1 proton that's in the hydrogen. So this is something that happens here. So a covalent bond where the electron pairs are roughly equally shared is a nonpolar covalent bond. And so that's that case of like the 2 hydrogens that are bonded together, is that they share their pair of electrons right in between them, then neither one pulls more strongly towards them, and so as a result it's balanced. It sits right in the middle there, and so that's a nonpolar covalent bond. But a covalent bond where the electron pairs are unequally shared is called a polar covalent bond, all right? And so we said a nonpolar covalent bond is one where, you know, they're equally shared. You can see those electrons, they sort of fill up a region around here equally on both sides. A polar covalent bond, the electrons are pulled more on this side. So remember, this is a shared orbital, right? And so because of the fact they're pulled more strongly towards the more electronegative element right here, is that means they're going to spend more time around here. They're going to spend more time on this one, less time over on this side. Because we can't say exactly where they are because it is an orbital. We're just describing the overall region where they're most likely to be found. But even within the orbital, they're going to be more likely to be found near the more electronegative one. And that creates an unbalance. And so this right here is a polar covalent bond. This right here is a non-polar covalent bond because this one sort of spreads out that electron pair sort of equally between the two versus this one where it's going to get pulled much closer to the more electronegative element. So how do we know? So here's how you do it. If the difference in electronegativities is less than 0.4, it's between 0 and 0.4, you can see that sort of down here, then the bond's considered to be nonpolar covalent. If it's between 0.4 and 2.0, then it's considered to be polar covalent. And of course, if it's bigger than 2.0, then basically that the one that's more electronegative straight out steals the electron and runs off with it from the cation. So that's sort of how we do that there. So the greater the difference in electronegativity, the more polar the bond. And so even though we said that, like, 0.4 is the cutoff, and so then a difference of 0.5 in electronegativities would be polar covalent, so is the difference of 1.9. But this is a lot more polar than this one is because there's a bigger difference in electronegativity. And what happens is, because the more electronegative atom has pulled the electrons closer to it, that atom will have a slightly negative charge, while the less electronegative atom will have a slightly positive charge. So we use that example that we saw before of the HCl. We said that the hydrogen that's in here has a low electronegativity, said 2.2. The chlorine has an electronegativity, we said, of 3.16. And so that means that that electron pair is going to be much closer to the chlorine here. And so because the electron pair is closer to the chlorine, it leaves, and it's going to spend more of its time sort of, once again, sort of surrounding this part over here, and less of its time over here. It means this side's going to overall have a negative charge, because those negative that electron pairs extra 2 electrons that are sitting over here. The hydrogen then, because the electrons have been pulled away from it, is going to have a slightly positive charge. So one end of this molecule is negative and one end of this molecule is positive. And so this situation, when you have a little separation of charge where one end is positive, one end is negative, is called a dipole. And so notice the di meaning 2, pole meaning pole, of course, positive, negative poles. And so it has 2 poles, one negative pole, one positive pole. The more polar the bond, the bigger the difference in charge between the more electronegative and less electronegative atom, and the stronger the dipole. So if you only had an electronegativity difference of 0.5, this would not be very polar. There would be a slight negative charge on one side and a slight positive charge on the other one. But if you had a 1.9 like this, you're going to have a big negative charge on one side and a big positive on the other one. But it's still not enough to actually pull the molecule apart. Is that they're still going to be shared, is that it's just one has taken it a lot more strongly. It's sort of like, we look at our little cartoon over here, is that these two atoms are still sharing these 2 electrons, even though our amino chloride over here, very electronegative, has pulled them very strongly towards it. They're still shared, just like these are shared. It's just these are shared very equally between them. They sit halfway in between because both of them pull towards each other with equal amounts, versus these 2 are being pulled much more strongly towards that chlorine right there. And so as a result, this molecule of the 2 hydrogens is going to be nonpolar. This molecule over here of the chlorine hydrogen is going to be polar. And what we're going to see out of that polarity is that because the electrons are going to get pulled over to this side here, this end's going to be somewhat negative, this end's going to be somewhat positive. Now to show that whenever we draw these out, the way that we actually indicate how positive or how negative they are is by using these two symbols. We use a delta minus and a delta plus. That little squiggly symbol here is the Greek letter delta. Looks like that's a lowercase delta. Remember, uppercase delta means change in, looks like that, but that's lowercase delta. So if you do a delta minus, that means it has a partial negative charge. A delta plus means it has a partial positive charge. And so really the way we would write these out here is to show what this looks like is we would basically say that this is going to be delta minus over here, this is going to be delta plus to indicate that this side has a partial negative charge, this side has a partial positive charge like this. Of course, our two hydrogens that are over here on the other side don't get that at all because they're not polar. It doesn't form a dipole of those two guys. So let's take a look at some examples. So HF, hydrogen fluoride, has an electronegativity difference of 1.9, just barely under the mark to become polar, to be ionic. And so you can sort of see that, it gets covered up down here, but that's this guy right here. And so we have the hydrogen on this side, we have the fluorine that's on this side. Fluorine is much more electronegative, it's going to pull those electrons towards it. The red indicates that it's more negative, the blue indicates more positive. And so we would say that this end right here is going to be delta minus, this end right here is going to be delta plus. We know it's going to be a polar covalent bond because this is above 0.4. And so definitely going to be polar covalent because 1.9 is definitely above 0.4, but it's less than 2.0. HCl, the difference in electronegativity is a lot smaller, 0.9. You can see that it's not as red on this end, not as blue over on this end right here, but still it's above that 0.4 mark. And so as a result, this is still going to be a polar covalent bond. This end right here, because the chlorine's the more electronegative, chlorine's over here, the hydrogen's over here, chlorine's more electronegative is going to be delta minus. This end right here is going to be a delta plus right here. HBr, 0.7, still above 0.4. We consider it to be a polar bond. Not as polar as the other one here. This is still going to be a delta plus. This end is going to be our delta minus. So there's just a slight polarity. It's a slight dipole, not nearly as strong as this guy or as strong as this guy. This one's much weaker in terms of that because the electronegativity difference is not as big. So it's going to be a dipole, but not as strong. You can see, it's, once again, you can see the coloration is not as strong on the two ends. That's the way they've indicated here. Hydrogen iodide, right over here, right on the border. 0.4 for electronegativity difference is exactly, it's sort of like right on the border here. And if you look at this, you can see that there's not really a whole lot of difference between the colors on both ends here because those electrons are pretty evenly shared. And so it's right on the border of being just maybe ever so slightly polar. So there might be a delta plus and a delta minus here. But if it is, it's just a tiny, tiny bit right here. Now, we can see that these end up being more dipoles by using something called the dipole moment. The dipole moment shows how strong of a dipole it is. And you can see the ones with the bigger electronegativities have the larger dipole moments. The ones with the smaller electronegativities have the smaller dipole moments. So this is a weak dipole. That's a strong dipole right there. And so you can also see that the ones that have the stronger electronegativity differences also have shorter bond lengths. They're stronger, they're more stable bonds. The ones that typically have less electronegativity difference don't pull the electrons in as tightly compared to each other, and so as a result have a little longer bond length. They're not quite as stable. All right, so let's look at some properties. Covalent compounds tend to have a few distinctive properties. One, they're generally gases, liquids, and or solids that have low melting points. So ionic substances tend to have high melting points, tend to be solids. Covalent compounds, gases, liquids, and if they're solids, they have low melting points. Nonpolar compounds dissolve well in nonpolar solvents, but not in polar solvents. But polar compounds dissolve well in polar solvents, but not nonpolar solvents. So nonpolar means it has those nonpolar covalent bonds. Polar compounds means that we have the polar covalent bonds. And so which one they dissolve in depends on which type of bond they have, whether it's nonpolar covalent, in which case it only dissolves in nonpolar substances well. Polar covalent means it'll dissolve in polar solvents, but not nonpolar. Last thing we have here is whenever you melt or dissolve a covalently bonded compound, they don't conduct electricity well. Very poor conductors of electricity. So let's break these down. So they're generally gases, liquids, and solids with no melting points. Why is this true? Well, remember we said the forces between atoms inside molecules tend to be very strong, but outside molecules tend to be weak. And so if I have two molecules, if I have two oxygen molecules here, double bonded to each other, and so this is very strong inside the bond, so that's a very strong force that's attracting those two to each other, very strong here, but the force that goes in between these two is really, really weak. And so because it's really weak, how difficult is it to pull these two molecules apart from each other? It's very easy to pull them apart. And so oxygen, as a result, is a gas. That's what we breathe in. They aren't very strongly attracted to each other because the strong forces, the strong attractions are inside the molecule, not outside from molecule to molecule. So it doesn't take much energy to pull them apart to make them melt. It doesn't take much energy to evaporate them. And so as a result, they tend to have low melting points. They tend to be gases or liquids. Now, polar molecules, okay, ones that are these polar covalent bonds, they have higher melting and boiling points than nonpolar molecules, but they're not as high as ionic substances because the positive end of one dipole will pull towards the negative end of the other dipole. So if I have like HCl like this, and I have two HCl molecules, we said this is, if you look at the electronegativity difference in this, hydrogen we said was 2.2, chlorine has an electronegativity of 3.16. The difference there is about 1 for its electronegativity, so it's definitely going to be polar covalent. And if it's polar covalent, the more electronegative one, this chlorine over here, is going to have the slightly negative. The hydrogen is going to have the slightly positive. And over here, this hydrogen is still the slightly positive. This chlorine's a slightly negative. And so what's going to happen? There's going to be a stronger attraction between the positive one end of one dipole and the negative end on the other dipole. So those are going to pull together a little more strongly. And if they pull together strongly, it takes a little more force to pull them apart. And if it takes a little more force, it takes more energy to pull them apart. And so you have to get them hotter to melt. You have to get them hotter to boil. It's going to take more energy to bring them apart. So they're more likely to be solids. If they are polar molecules, they are more likely to be gases if they are nonpolar molecules. And so this is sort of the reasoning behind why these work out the way they do. Next one we had, nonpolar compounds dissolve well in nonpolar solvents, but not very well in polar solvents, while polar compounds dissolve well in polar, but not nonpolar. So like dissolves like. This is the rule that we will learn later on here if you have trouble remembering all these words here. Like dissolves like. But why? Why does like dissolve like? So for nonpolar compounds, only nonpolar solvents dissolve well because the molecules in polar solvents only attract to each other, not to the nonpolar molecules. So if I had some so my solvent molecules are out here. So because the fact that they are polar is that they have their little delta minuses attracting to their delta pluses, they like to play together because they are attracted to each other. And then there's a delta plus right there, and they attract to each other. But these little nonpolar molecules here, they can't break up that party. So all these polar guys are going to attract to one another. They're not going to attract to these guys at all. And so as a result, that polar solvents don't generally dissolve nonpolar solvents or nonpolar substances. So if you had something like H2 and you said, well, how well would that be dissolved by water? Well, not very well, even though it is a gas. But still wouldn't be dissolved very well by water because that water is a polar substance. It has polar covalent bonds. Those bonds make the water molecules stick to each other. They're not going to attract very well to those the H2 molecules, which have a non-polar covalent bond, are not going to be able to break into that. Okay? But for polar compounds, on the other hand, polar substances dissolve them really well because what's going to happen is now, instead of having the situation where these are all non-polar down here, the new polar molecules, which we'll try to draw in red so we can see what's going on here. So here's our polar molecule. What's going to happen? Well, hey, if this end is going to be negative, then this end is going to be positive. Then what's going to happen is that this negative is going to attract to that positive, and it's going to get pulled into the solution. And so it's going to get ripped apart, and it's going to get separated, and it's going to get dissolved whenever that happens. So that the positive charges of the molecules attract to the negative charges of the solvent molecules, and the negative charges of the negative ends of the polar compound molecules are going to attract to the positive ends of the solvent molecules, and that pulls it apart like that. And so that's the reason why they do that. So last one here is when melted or dissolved. These do not conduct electricity very well. Very poor conductors of electricity when we talk about covalently bonded substances. The reason why is that they don't break up into ions. Is that even if you have something like HF, just about the most polar substance that you can get that's covalently bonded. So we said all the electrons are hanging out next to fluorine because it's so electronegative. We have our delta minus here, our delta plus here. Overall, if you look at this whole thing, what's the total charge? 0. No charge, because of the fact that they're shared electrons, that this does not have an overall charge. And so because of that, even if you have these dissolved into a substance, there are no charges. These don't have charges to flow around, unlike ionic substances where you have some Na plus ions or whatever that's a positive charge. That positive charge can flow one way or flow the other to carry electricity. This has 0 charge, and so since all covalent compounds have 0 charge, they're electrically neutral. And if they're electrically neutral, their flows don't create electrical current flows. And so it's a quick way of telling if you have an unknown substance. You say, is it ionic or is it covalent? Dissolve it. If it conducts electricity, then it tells you it's covalently bonded. If it doesn't conduct electricity, or if it does conduct electricity, then you know it's likely to be ionically bonded.